In this sixth and final module, we'll now begin to explore some of the Vibrio forecast and other products of our research on climate change, and we'll specifically be talking about virulence of some of these Vibrio organisms. As this slide shows, just as we ended the last section with our harmful algal bloom forecast, we now see that we're able to produce Vibrio forecasts that allow us to predict Vibrio change. This happens to be a forecast for the Chesapeake Bay. And so this allows us to give both a nowcast 3-day forecast and then a 14-day and monthly forecast so that people can take appropriate actions to avoid Vibrio exposure in the future. The next factor of climate change that we'll talk about is increased sea level rise. And this can cause both increased coastal flooding and subsidence. It can result in a destruction of property, particularly infrastructure, things such as water, sewer, and other critical infrastructure within the coastal zone needs to be hardened and resilient and placed in places where it will be not prone to flooding, damage from tropical storms, hurricanes, and sea level rise. Things like sewage treatment plants, which can discharge pollution into the environment. This next slide shows the change in sea level, the rate of sea level rise over time. And as you can see, we're now into this ecstatic, this period of sea level rise where things are sort of unprecedented. We're seeing what would normally be a small rate of sea level rise due to eustatic sea level rebound with slight sea level rise with land rebounding up in elevation and sinking with coverage by seawater. We now see that we have reached this period with climate change where we're seeing even greater rates of sea level rise than we would normally anticipate. What may be 10 centimeters 100 years may be 100 centimeters in 100 years. This next slide sort of illustrates this point. If we take a look at the slide in the left, that happens to be a police vehicle that is one of Charleston's finest. And that is a slide taken just outside of the NOAA lab on Fort Johnson here in Charleston on a afternoon thunderstorm which fell in an urban area at the time of high tide, and there was nowhere for the water to go. And so as you can see, not even Charleston's finest could get out of the way of that rapid rate of water elevation that rapidly increased. And so this just sort of illustrates how the complexity of urbanization and some of the things that we see with sea level rise coming together to create conditions with sea level rise that really make it, coastal enterprises very vulnerable, both industrial areas as we see in the middle slide, or urban areas as we move out to the edges on the far right. One of the things we're most concerned with is the ability to provide adequate drinking water supplies. Now this happens to be a map of Winyah Bay located at Georgetown, South Carolina. And in this portion of the slide where I have the cursor, this is the drinking water intake for the city of Georgetown right in here. And so one of the things we have done is we have undertaken a study looking at the levels of Vibrio bacteria out in, and these are Vibrio vulnificus and parahemolyticus in yellow and white respectively, and these are the average annual densities at each station location. And so really your upper end of saltwater intrusion is right about here, but as you can see we have measurable levels of Vibrios for 10 to 15 river miles upriver, and including in the area where the drinking water intake is for the city of Georgetown. So one of the things we began to try to do is to build models to predict changes in salinity associated with sea level rise and climate change to forecast future Vibrio levels up in this area of Winyah Bay and the Waccamaw River, including the drinking water portions of the Waccamaw River. These are the number of Vibrio bacteria found in bottom water. Vibrio vulnificus is in blue, Vibrio parahemolyticus is in red, and this is moving from April through October of the year. And we have in yellow the effect of temperature, and you can see that with Vibrio vulnificus, our peak abundances occur with the peak temperatures, whereas with the Vibrio parahemolyticus, we don't see that same trend in terms of the numbers of Vibrio parahemolyticus following the increase in temperature. They're pretty uniform levels and they vary over time. Similarly, if we plot Vibrio vulnificus in blue and Vibrio parahemolyticus in the orange here with salinities, you'll note that salinities we see for Vibrio vulnificus, we see peak abundances at mid-range salinities of 15 to 25 parts per thousand, whereas with the Vibrio parahemolyticus, the numbers stay pretty uniform regardless of the salinity. So not all Vibrios are created equal, and some vary directly with temperature, some vary directly with salinity, and that's why understanding climate change and temperature and sea level rise all go hand in hand. From these monitoring data for Vibrios, we were able to put together an algorithm to actually predict Vibrio vulnificus levels within this watershed using measures of conductivity, which is intimately related measure of saltwater intrusion related to salinity, turbidity, and temperature. And with those three variables in our model, we could explain more than 62% of the variance in Vibrio vulnificus densities within this watershed in Winyah Bay and the Waccamaw River. We were then able, working with the U.S. Geological Survey as well as the CISA Climate Center at USC, able to put together a surface water salinity intrusion model that basically integrated the PRISM model to actually estimate the changes in precipitation associated with some 11 different global climate models, so that we could talk about the changes in freshwater input into the watersheds draining this Waccamaw Winyah Bay area, along with a sea level rise model, which will be illustrated in the next slide. So we were able to put together this integrated model. Using the PRISM exam model to predict increased amounts of freshwater input or lack of freshwater inputs during drought, or increases in freshwater input during major rain events, we were then able to put that with a sea level rise model to create a neural network model that allowed us to integrate both sea level rise and global climate change predictions on precipitation into a predictive algorithm for salinity that could be used in temperature, that could be used to predict Vibrio levels within the watershed. So this is a slide depicting, with no change in sea level, a 1 foot change in sea level, a 2 and 3 foot rise in sea level over the next 50 years, what the frequency of high salinity events as measured by specific conductance would be. And these spikes in salinity represent optimal growing conditions for Vibrios. So as you can see, the number of optimum growing conditions for Vibrios is dramatically increased at this particular station, which happens to be some 10 to 15 miles upriver in the freshwater part of the Waccamaw River. Again, by taking that data from sea level rise, we were then able to use the downscale climate models through this neural network model to run both a hindcast, that is a historic look back to see how our data correlated, and then a future look ahead from 2040 to 2070 to predict the changes in salinity and Vibrio abundance within the watershed. This next slide depicts the algorithm we use to predict Vibrio vulnificus, which utilizes salinity and temperature to actually predict the future change in optimum growth conditions for Vibrio vulnificus. And you can see again with no sea level rise, a 1, 2, and 3 foot increase in sea level rise, you'll see more than a tenfold increase in spikes of bacteria predicted abundances of Vibrios, which represent optimal growth conditions for Vibrios. So just as we saw with the salinity being optimal, we also see the Vibrio levels being optimal. Now what's interesting about these two predictions, it clearly shows that what would be the drinking water for Georgetown is going to be salty water, which we will not be able to drink without additional desalination possibly. And we also see the effect will be that there will be increased pathogens in the form of Vibrio vulnificus in the drinking water that would be a risk to human consumers of that water. Another factor associated with sea level rise, because of the fact that sea level will rise and increase the amount of soil moisture within coastal soils, this will likely increase the amount of contaminants, microbes, and nutrients running off of coastal areas. That's because most of the current models that predict runoff use only a 50% soil saturation level. If you increase the soil saturation levels to higher percentages of soil moisture, which will likely happen as sea level rises and fills in all the soil pore spaces, you might expect to see much greater levels of runoff of these contaminants during rain events. One of the things we see when we look at heavy precipitation events, we are seeing that there has been a significant increase in what we call heavier precipitation events. In fact, in the southeast U.S., we have already seen in the last 15 to 25 years a 20% increase in the number of heavy precipitation events and even more dramatic changes in the northeast U.S. What this means is that when it rains, we have greater intensity of rainfall because of the increased thermal dynamics in the atmosphere to produce that rainfall. So that means that when it does rain, we're having heavier rain events when it does rain. This slide depicts an area on James Island, South Carolina, the same place where we saw the police car caught up in the afternoon thunderstorm and being flooded. This area has 31% impervious cover, and under that runoff condition, 29% of the rainfall would run off as opposed to 10% for a natural area if this area were not urbanized. You'll notice that with increasing sea level rise, which would cause greater wetting of the soils and higher proportions of the soil spaces covered with water, we can see that the runoff would increase dramatically, over 159% increase in runoff without any additional urbanization in this watershed, simply from the effect of the increasing soil moisture associated with sea level rise. Also, we note that during periods of drought, the amount of soil moisture would go down, and so the levels of runoff would be much lower. So what this slide depicts is the extreme nature of the weather and how in periods of high levels of sea level rise, we can expect to see very much higher rates of runoff of chemical and microbial pollution. These data are again from Dr. Tom Peterson, and it depicts changes in precipitation projected for the end of the century. And these projections are not as accurate as temperature projections, but I think if you look, most of the color that we see in the southeast U.S. is white or brown, and if you look at the scale, what that generally means is drought. So as you can see in the winter, spring, and summer, we will generally have drought conditions. The only time we may see a little bit of let up is in the fall when we have tropical storm activity, which may cause more precipitation. So by and large, the main change in precipitation patterns associated with climate change forecast in the southeast and for most of the U.S. is going to be increased drought. Now, the Centers for Disease Control conducted a workshop and projected some of the problems associated with drought. They include compromised water quality and quantity, particularly water quantity and the quality of that drinking water in particular, compromised food and nutrition, compromised air quality because particulates will build up in the air and will not be washed out, and that can include harmful algal blooms as well as chemical pollutants. Diminished living conditions, things such as increased temperature and other factors may render areas not as easily to reside in, not as easy to recreate in, and quality of life issues. Increased recreational risk. For example, we know some of the organisms like Naegleria fowleri, which is the amoeba that causes infections in the brain, can be increased during periods of drought. And then increased disease incident for infectious and chronic and vector-borne diseases. So infectious agents like E. coli, salmonella, chronic illnesses like asthma, and then vector-borne diseases. Now, if we take a look at some of the ecosystem health impacts of drought, they include altered water quality, delivery, and water quality and quantity. So the altered water quantity, delivery, and water quality include effects on temperature, salinity, pH changes, increasing pollution loads during rain events, and they can also affect the airshed, affecting air quality due to the increase in wildfire potential, which may cause major air quality issues, increased particulate load in the atmosphere in between rain events, and then harmful algal bloom events, which may put toxic chemicals out in the environment from harmful algal blooms. This is a slide depicting the effect of drought in the southeast U.S. on the Atchafalaya River, which is a drinking water source for Atlanta, and the river ends in Apalachicola Bay, which is the largest or second largest oyster production area in the U.S. for seafood. And so what this slide illustrates is on the right, as you decrease the amount of discharge in the river from the dam to allow water to move down into Apalachicola Bay, we see increases in salinity that dramatically affect the shellfish harvest area. Now, as you might imagine, the 3 million people, 5 million people, however many there are in Atlanta, are clearly going to get the water during a drought, not the 30 or 40 shell fishermen in Apalachicola Bay, Florida. And there could be more than that, but bottom line is it's less than probably 100 folks involved in the shellfish industry. So the greater good is going to go to the folks that need the water and use it the most, and that will be in Atlanta. So as we wrap up this section, you can clearly see that the effects will be to increase salinities in Apalachicola Bay. In the final installment of slides, we'll take a look and see how salinity changes in Apalachicola Bay affect the shellfish industry itself and can cause increased Vibrio illnesses in the next segment.